Hi, folks. Next on our list is chapters 9 and 10, and they're really closely related. So I think it makes sense to talk about them together in one lecture. And more than that, I think it actually makes sense to talk about the content in the reverse order. Chapter 9 makes some emphasis on Isaac Newton's contribution to the study of gravity. And then in chapter 10, we talk a little bit about why that, like, the things about the study of gravity that mean that his contribution is so significant, which I think is backwards, especially because the things in chapter 10, at least the beginning of it, is the part that's familiar to us. It's the motion of objects, like here on Earth. So here's my plan, is to start with that and go through some of the material in chapter 10 and then circle around to some of this material from chapter 9. We're going to get all of it, but in one chunk, because I think that makes the most sense, and in the reverse order. I'll give you like a heads up when we transition from chapter 10, I guess, into chapter 9. So we're going to end up here talking about the Newtonian synthesis. That's this big contribution that Isaac Newton made to the study of gravity. And we'll, examine some of the consequences of this idea and talk about some things. And we will get there by way of talking about projectile motion, which is a fancy way of saying the motion that a thing undergoes here on Earth when we throw it. Let's start there. In the absence of gravity, Galileo had the idea about inertia. In the absence of other influences, other acting forces, in the language of Isaac Newton, if we give an object an initial velocity and then nothing else happens to it, it will continue moving with that velocity. And velocity is, remember, a word for which the direction is baked in. We aren't just talking about speed, we're talking about speed and direction, which means the direction that we're traveling remains the direction that we're traveling. We're talking about a straight line path. If we introduce gravity, then we know from experience, if we throw something that way with an initial velocity, that's great, but it isn't going to keep going straight line that way. Gravity will pull it down. It continues moving horizontally because it was moving horizontally. It has, you could say, horizontal inertia. And the fact that gravity pulls down, well, that's kind of irrelevant. Gravity pulls down, so we can accelerate the object down, just like we would accelerate a dropped object. But gravity pulling down doesn't get to affect the horizontal. It just adds a vertical story to it. So we throw something that way with an initial velocity, an initial horizontal velocity, and maybe I need to change what I just said. It does continue going that way with that velocity. It just also does other things, falls towards the ground like any other object would if we dropped it. It's like we're doing two things. It's like we're doing horizontal motion and vertical motion together simultaneously. We've got a horizontal component that constant speed, same direction, same speed, because there's no acceleration that way. Along the horizontal, there's nothing going on. Vertically, it's like any other falling object. It speeds up, and the distance between sequential dots here in the figure increases because we're speeding up. We've seen this picture before, at least the vertical story, and we've seen the horizontal story. Just now, we're going to do them at the same time. Horizontal motion without gravity in the first figure, vertical motion only in the presence of gravity. Okay, put them together. Do both simultaneously. We've got these same 6 dots across the top, and we've got these same 5 dots vertically. And at each step, each increment, each time interval along the way, we do both. We move to the right the same amount we've been moving. We move from here to here, and we move down the same distance we would have moved if we were just falling. So we move to the right and down, and we end up here. We do that again. We move to the right and down further because we're speeding up on the way down, like free fall. So we move to the next dot, which is further down, but the same distance to the right. And so on. Further down, mouse keeps disappearing. Further down, same distance to the right. Further down, same distance to the right, and so on. And if we put all that together, we end up with this curved path. We've seen this curve before, at least this shape. If we keep the horizontal component the same horizontal distance in equal times, the gravity doesn't act horizontally. So horizontally, it's like that projectile is still traveling that way in a straight line. It's just also doing free fall. It's just also doing free fall. The path of a projectile is the path horizontally or at an angle. It's the straight line path that would have been followed plus free fall. So each second along the way, we have to adjust away from the straight line path according to the distance we would have fallen due to gravity. So we launch the cannonball. A second later, we would have been here along this straight line if gravity weren't a thing. But gravity is a thing, so we pull it down and we ask, how far do we fall in 1 second of free fall? And the answer is 5 meters. So we are 5 meters below where we would have been. A second after that, how far have we fallen in 2 seconds? Well, the answer is 20 meters. Okay, so if we would have been here along the straight line path, we have to move ourselves 20 meters down because we've fallen 20 meters in the 2 seconds, and so on. We've seen this kind of shape before. It's a parabola. acceleration, change of speed only in the vertical, which that's the gravity direction, horizontally constant speed. So if we draw the components of the velocity, because at this instant, we aren't going up or across, we're going both. We're traveling that way along the curve, up and to the right. So our velocity has a two-dimensional direction, but we've done this trick before. We can resolve it into a vertical piece and a horizontal piece. That horizontal piece in each of these 5 instants along the path of this projectile, that horizontal piece is the same length every time. Because the horizontal story is one of constant velocity. The vertical story is one of free fall. Horizontal component remains constant. Only the vertical component changes. The actual velocity we could find if we have the two components, we can find the hypotenuse with the Pythagorean theorem. And if we needed the direction, we could find it with some of that right triangular trigonometry that we discussed a couple weeks ago. But if we need to know how fast is this thing moving at any given instant, well, if we have the horizontal and the vertical, and there's no reason we shouldn't, because we know how to talk about the change in velocity for constant velocity. Well, horizontally, there isn't any change. As long as we know the horizontal velocity we started with, we know the horizontal velocity the whole time. And as long as we know the initial vertical velocity, then we have equipment. We've got formulas to figure out, okay, what time is it now? Let's say here, what time is it now relative to where we started? Okay, whoa, what time is it now relative to where we started? So what is my vertical velocity now? Which we've got formulas for that. And we could find the two components and Pythagorean theorem, find the hypotenuse of that triangle to figure out how fast we are going at any given instant. Now, if we can exclude the air resistance, things are symmetric. You know, we think about sayings like what goes up must come down, and it implies a certain symmetry to it. And what is the story going up is the story coming down, as long as there aren't any other effects like air resistance, for example. So the timing is symmetric. The horizontal distance traveled from one point to the other is also, symmetric. I mean, it's a parabola, right? But the shape of that parabola depends on the initial angle at which we launched the thing. And you can see that in the absence of air resistance, which is what this slide is showing, the largest possible horizontal range is found at 45 degrees of launch. Now, we don't exist in a vacuum. So that's only for for an ideal launch without any other effects or air resistance or anything like that. For sort of terrestrial objects like a baseball or a golf ball or something, we might need to account for air resistance. And with a lot more math than we are ready for, we can show that the maximum horizontal range is obtained for a hit baseball at something around 30 degrees, actually, instead of 45. For a golf ball, it's a little bit greater than that, but it's still not 45 degrees. Basically, if we launch the projectile with too much up, there's too much air resistance, and it slows us down too much, and we don't travel as far horizontally. If we launch at a lower angle, closer to horizontal, more of our initial velocity is in the horizontal direction. And we can sort of push through that air resistance a little bit better. But there's a point at which we're too close to the ground, too shallow an angle, and we just hit the ground too soon to actually travel the horizontal distance that we could get to, because gravity is going to pull us down the same rate regardless. So, I mean, that's why there's the optimal range, and they're different for different objects because air resistance affects different objects differently. Okay. So we have talked about the motion of objects that are thrown near the Earth. This is true. For motion over level ground, right? Because this symmetry is true to return to its initial level. If that's the ground, then we're assuming that it returns to the ground because the ground is flat. It goes up and comes back down, and it travels to the same point because that's the ground. But the surface of the Earth isn't actually flat because the Earth is not flat. So how important is the curvature of the Earth to this projectile question? How much do we need to account for the fact that the ground isn't technically level? Makes me think that if we could throw an object fast enough so that as gravity pulls it down, the curvature of the Earth curves away from the horizontal. Right, here we are standing on the Earth, and we throw something super fast, and we throw it so that as gravity pulls it down, the curvature of the Earth curves away from horizontal. And as it falls towards the Earth, so does the Earth's surface curve, and it falls around the Earth instead of hitting the surface. If we throw it with too little speed, we end up with a parabola. If we throw it with just the right speed, then as gravity pulls it down away from the straight line path that it would have, as gravity pulls it down from that, if the curvature of the Earth sort of matches the shape of its trajectory, it'll never hit the ground, and we never get the like edged effect of a parabolic shape. It's sort of straighter on the sides than it is at the top, but we never hit the ground, so we never get that behavior. We just get circle. The Earth is spherical, so if we at all times match the the falling rate, I guess, matches the curvature of the Earth, then we get to travel around the Earth that way. As long as we can avoid air resistance and, you know, buildings and trees and stuff. If I tried from here to throw something, I would encounter way too much air resistance and way too many obstacles for this to actually happen. I'd have to be at some altitude, ideally beyond, just beyond the atmosphere, where we can argue that there is no air resistance because there is no air. The International Space Station is right about where we want to be. There's a little bit of drag, a little bit of air resistance on the space station, and it does need to be boosted into stable orbit occasionally. But that's basically right where we're talking is 150 kilometers or so. In such a state, we are always above the ground. We're moving across the ground. We never move towards the ground. Gravity is pulling us towards the surface of the Earth, but we never actually move towards the surface because we're falling around the surface. We are always moving around a circle as opposed to inward, which makes me think about makes me think about motion of a thing in a circle. It makes me think about centripetal force. And anytime we have, just like that, anytime we have a force pulling circularly inward, like gravity, and we're moving in the circular path. Now, the circle itself is always perpendicular to the radius direction. So here, for these hyper fast thrown objects, if we end up in this stable situation where we can fall around the Earth, then what we're doing is moving in a direction perpendicular to gravity. We're talking about circular motion. How fast are we talking? Well, the Earth has a curvature, roughly, so that for every 8,000 meters of horizontal distance, there's a 5-meter difference between where the surface is and where it would have been. So how fast does it need to be going? Well, it needs to match the curvature. It needs to, so, okay, wait a minute. a projectile is going to fall like it's in free fall. Gravity will pull on that thing, and we looked a second ago at the path of the launched cannonball, and we said 1 second after it's launched, it has fallen 5 meters away from its straight line path. But that's the same 5 meters as in this picture. So if we could launch a thing fast enough so that, well, if it's able to travel 8,000 meters in a second, that means that by the time it has fallen 5 meters away from its straight line path, the Earth, the surface of the Earth, will also have curved down by 5 meters. So we won't hit the ground because the ground will have moved by the same distance that we fell. And what we'll do is end up skimming along the surface here, not actually, hitting the surface. We'll just fall around the surface because we are going to fall, according to gravity, in exactly the same way that the Earth is curved. So we'll never hit the ground. 8,000 meters per second. Just out of curiosity, I don't have a really good, that's 8 kilometers per second, which sounds like a lot. – 8,000 meters per second is just about 18,000 miles per hour. Okay, so I'm not going to be able to throw any object to do that. We can, some of the fastest, like, human propelled objects are going 100 miles an hour, maybe. Think about fastball baseball pitches, or maybe a tennis serve or something like that. 100 miles an hour. Now that's in air resistance, so that's thing number one. If we were high enough that there weren't air resistance, I don't think we could still get to 17,000 miles per hour. But if we had if we had a rocket or something, we got to do two things. We got to get it to altitude above the atmosphere, about 150 kilometers or so. And then once we're there, we've got to tip into tangent, just tangent to a circle. We've got to point in the circumference direction, and then get ourselves to a speed of 8 kilometers per second, and we will fall around the Earth. Okay. So any less than that, and we will eventually hit the ground. We'll kind of spiral inward, or we'll just see a parabola if we go slowly enough. What if we go faster than this? Well, it won't be a circle anymore. It'll be an ellipse. If the speed is greater than needed for circular orbit, the satellite will overshoot a circular path and move farther away from the Earth. It's still subject to the Earth's gravity, and eventually the Earth will change its direction and slow it down enough that we can start to pull it back the other way. So we slow down and turn around, and then speed up and come back. And it does repeat a stable elliptical orbit, but it just isn't circular. That's no problem. And we actually have a lot of the equipment we need to talk about what's going on in this situation, because we've talked about energy. We are way outside the atmosphere at this point. There's no way for anything other than gravity to change to affect the motion of this satellite, which means there aren't any non-conservative forces acting. The only force that's acting is gravity, and we know that gravity conserves energy. So however much energy we have when we start the orbital motion, we will keep. If we are moving, then we have kinetic energy. And if we are above the Earth's surface, then in that configuration, we have gravitational potential energy. The total energy we have is constant. We can trade back and forth from kinetic to potential, but however much total energy, the total mechanical energy, kinetic or potential, that we started with, we will keep. Now, in circular orbit, we never change our configuration relative to the Earth. We are always the same distance away from the Earth because it's a circle, which means our gravitational potential energy is never going to change, which means our kinetic energy can't change either, because we would have to trade one for one, but we're never going to gain or lose any potential, so we can't gain or lose any kinetic either. So our speed the whole time is constant because our kinetic energy is constant. Now, in an elliptical orbit, the story is a little bit more complicated because we move farther away from the Earth sometimes. And the farther away we move, the more potential energy we have. Now, if we're gaining potential energy moving farther away, that means we have to decrease our kinetic energy because there's only so much mechanical energy to be had. And if we're allocating it to potential, we had to take it away from the kinetic. And that's what they're trying to show us here with the relative sizes. At these 2 points, we've got some kinetic and some potential. Later, when we are very, very, very far away, at the farthest point, which we call the apogee, APO is the prefix for really far away. It depends a little bit what we are far away from. What the word is, apogee, is the word that we use to specify orbit around the Earth. Think geology, the study of the Earth. So apogee is far away from the Earth. If we wanted to talk about orbit around the sun, then we would talk about the aphelion or the perihelion. I'm trying to, there was a Roman or a Greek deity that was Helion or Helios or something like that. Anyway, about some sort of name for the god of the sun, I suppose. And that's so. If we're talking about solar orbit, then we wouldn't say apogee because it's not G, it's Helion. But anyway, the point of farthest distance from the celestial object that we are orbiting, I suppose, we have the most potential energy we will have, and our kinetic energy is less. This KE right here should actually be smaller than this one. And this PE should be smaller than this one, because when we are very, very close to the planet at the point of closest approach, the perigee or perihelion, we have the least gravitational potential energy because we're as close to the surface as we're going to get. And therefore, in order to keep the total energy constant, because energy has to be conserved in this situation, our kinetic energy has to be greatest. If our speed is changing, that means our kinetic energy is changing. And that means that something is doing work, right? Because the work energy theorem says that net work done is equal to the change in kinetic energy. So if our kinetic energy is changing, that must mean that something is doing work. And the only force that's acting is gravity. There is a component of the gravitational attraction. The planet, let's say, pulls on the satellite. The Earth pulls on the moon with a force this way. And there is some component along the direction of motion, but a force along the direction of motion can change the speed. So that component is the component that speeds things up as we're coming back around from apogee, if it's the Earth, to perigee. The component of the force that's perpendicular to the direction we're going at any given instant, that's the component that changes the direction that we're traveling. Because you can sort of see the direction that we follow isn't this, always in that particular direction. Sometimes later we're traveling in a different direction, tangent to the elliptical path. So our direction must have changed. And it's the perpendicular component that talks about that. So it's the component parallel, tangent to our, parallel to our velocity at any given instant, which is to say it's the component that is tangent to the elliptical path that changes our speed, and it's the component perpendicular to that changes our direction. It's possible, go back a few slides, it's possible to go so fast that by the time we would turn around, we're so far away that gravity can't act strongly enough to turn us around. And we can say that we have escaped the gravitational pull of the Earth. And the Perseverance Martian rover has been in the news a lot here lately, and the launch that began the story left Earth with greater than the escape speed. And if we are leaving, maybe not the gravitational influence of the Earth, but that of the sun, then we can say we're leaving the solar system. We're far enough away that the gravitational influence of the sun is small enough to be negligible, and we have escaped. In 1972, Pioneer 10 was launched, and it was the first object, the first sort of man-made object to escape the solar system, because it was given enough speed, so it had the escape speed for the sun. It was able to escape the gravitational influence of the sun. We were not able to propel it to that speed. We used, not without a whole bunch more fuel, that would have made it a lot more heavy and much harder to do. So we used the gravitational attraction to Jupiter to pull the probe a little bit closer to Jupiter. And as we got closer to Jupiter, we sped up. As we sped up fast enough that we didn't make stable orbit around Jupiter. We overshot orbit around Jupiter, but we had sped up enough that we sort of got whatever the slingshotted, slang shoot, whatever the past tense of slingshot is, out of the influence of Jupiter and out of the solar system entirely. It took 11 years, roughly, for Pioneer 10 to actually leave the solar system from launch on Earth. Just a second ago, I made a claim that if we launched fast enough, if we launched with escape speed, we could go far enough away from the Earth that the gravitational attraction to the Earth isn't strong enough to turn us around and we can get away from the Earth. First of all, how do I know that the strength of the gravitational attraction that the Earth, exerts on me, on a probe, gets weaker as I get farther away? How do I know that? And then, okay, well, how far away do I need to be in order for that to be small enough that I can't change? How do I know that elliptical orbits are possible even? And it is not necessarily, because we threw a bunch of objects, or used rockets to launch them into orbit around the Earth to see what happened. We had been studying the orbit of celestial objects, planets and stars, for years. It was Kepler as sort of he was a grad student, essentially, working for the astronomer Tycho Brahe, who used Brahe's data to sort of show that the motion of planets around the sun was elliptical and not circular. From the data, from astronomical measurements through telescopes, that's all we're doing. There's no theory crafting here, but it's really impressive because this was in, I don't know, the 1500s maybe, with the technology available in the 1500s. This is quite an achievement. Based on the data, Kepler was able to publish 3 reliable laws of planetary motion. Planetary orbits are elliptical, and the sun is at one of the 2 foci. Now, what about the foci? That's the 2 points that are thumbtacked to the table that we're using to draw the ellipse. So these 2 foci, one of them, according to Kepler, is the sun. Second law. If we draw a line from the sun to a planet at point A, and then later we draw a line from the sun to the planet at point B, and we use those 2 lines that we drew as the boundaries of a weirdly shaped slice of pizza, this thing. Oops. The amount of time that went by between point A and point B, if we keep track of that amount of time, and then if we consider point C and point D, if the lines that we draw for point C and point D, if it takes the same amount of time to go from C to D as it did to go from A to B, then the area of those pizza slices is the same. So the line drawn sweeps through area, makes pizza slices of the same area in the same amount of time. The square of the orbital period. Now, what? So, okay, so the period is how much time it takes for one full orbit. How much time it takes for one full orbit. The square of that. So record how much time it takes to go all the way around from point A back around again to point A. Take that much time and square that for every planet. The answer you get will be proportional to what you get if you find the average distance between the planet and the sun. So sometimes it's close, sometimes it's farther away, but if we average that out over the entire ellipse, the average distance, raise that to the 3rd power, cube it, in other words. So whatever the distance is, multiply by itself and then by itself again. And that number turns out to be proportional to the other number we got, which was the square of the amount of time it takes to make one full orbit. And let me say this again. Kepler was able to demonstrate these 3 things from data alone. which is kind of remarkable. That is a pretty wild relationship to sort of hypothesize to see if it works. It's um, it's really quite something. Officially, those are the slides for chapter 10. So the next slide is starting the content for chapter 9. That doesn't make any sense to me. That's why they're all here in the one presentation. We have the ability to say some of what we did about a projectile entering satellite motion around the Earth because of Kepler, because of Newton. Projectile motion, the motion of a thrown object on near the surface. We have loads of data, loads of experience, right? We have an intuition for it. If I toss that, it's a mouse. I don't want to drop it, but if I toss something else, something I got on the desk here, I can almost catch it without looking, right? Well, I didn't that time, but if you see it, you can look away and you can almost catch it without looking because you know where it's going to go. We have an intuition for projectile motion. It's like if you're trying to catch a ball or a frisbee or something, you look up and then the sun's in your eyes and you can't see, and you still know to reach up and close the glove around the baseball. Well, how did you know it was going to be there? Well, because it follows projectile motion. So we have experience with that. We have intuition. And we have some way of assessing the curvature of the Earth. So we can put that together and say, well, okay, well, if I were able to go fast enough, maybe I could achieve orbit around the Earth. And that's fine. But I look up there and I see the sun, and I see the moon, and I see the other planets, and I see the stars, and they are out there, right? That's a whole other thing. And I don't have any intuition for that. I don't have I have no direct experience with what controls the motion of all that stuff out there. In fact, for a lot of years, we got it completely wrong. Because we see the sun make an arc across the sky, we say, oh, the sun is moving around the Earth, because that's what it looks like. We can be forgiven for that. That is exactly what it looks like. I mean, we know that it's not true, It appears that that's what's happening because the Earth is spherical and because it's rotating. So as we rotate, we see the point that is the sun, we see it go around in our vision. Okay. But that's because it's out there, right? And we can't we can't make direct observations about what's going on out there because it can't get out there. Certainly not in the 1600s. So in the time of Kepler, in the time of Newton, we have the terrestrial, right? We can make measurements on objects as affected by gravity here on the Earth. And we can say, oh, sure, free fall and inertia and heavier objects fall at the same rate because acceleration due to gravity, and we can do all of those measurements, everything that we've said. But that all is here, not out there. And the motion of what's out there, Kepler, we can make our observations, but the why, Kepler says nothing about why. Each planet orbits the sun in an elliptical path. Why? I don't know. That's what happens. That elliptical path is orbited in such a way that a line from the sun to the planet sweeps out equal areas in equal times. Why? I don't know. It's what the data shows. Third law, the square, the period is proportional to the cube at a different distance. Well, who knows why? It's just what happens. Here on the Earth, objects fall because gravity. We can talk about why. Galileo was talking about why. Isaac Newton did not discover gravity. The idea, now I make some fun out of the fact that every single thing, it seems like, is named after Newton. Because we do name a lot of things after Newton. But this is a thing that I'm happy naming. Like this is a thing for which someone should be named. This is a radical idea. That the Earth's pull, the gravitational pull on an apple, is the same, also means that the Earth is pulling on the moon. This is a radical idea for the time. That the interaction of sort of earthbound objects, terrestrial objects, the boring, the mundane, the everyday, that the motion of those objects are governed by exactly the same interactions that govern the motion of the heavens themselves. That's crazy. Why should that be true? This is the here. That's the way the hell out there. Why should they be related at all? What an idea to have. The same set of laws applies to both celestial objects and terrestrial ones. That's Newton's synthesis, and it is a big deal. The scientific community went, well, and the community at large kind of went nuts. This was like I said, this was a radical proposition. And Newton was challenged. He had to delay publication of this idea because he knew that there was going to be resistance to this idea. And he had first to develop the mathematics to prove that this idea was correct. When he published, I mean, this was like, I don't know, maybe over a span of 10 years it took to refine these ideas. When he published, he was able to argue, here are these laws of motion. And we have established them, F equals ma, inertia, equal and opposite. We've established these laws of motion for terrestrial motion. If we include a law of gravitation with those if those things are presumed to be true, I can show you terrestrial motion, and I can prove Kepler's 3 laws governing planetary motion. Those 3 laws that came entirely from the data with no sort of theoretical argumentation at all. Just here's what the data shows. I had no choice. This thing's proportional to that thing. I don't know what to tell you. And here comes Newton saying, I can show you why. I can prove, if this thing is true, that Kepler's laws must be true as they are, which means my idea has got to be true, because it explains why Kepler observed what he did. Every body attracts every other body with a force directly proportional to the product of their 2 masses, and that is inversely proportional to the square of the distance between their masses. That's it. Let me say it again. The force of interaction between 2 masses, the gravitational attraction between gravitational attraction between 2 masses is a force. Now, and that word means a thing because it's in the context of Newton's laws. The strength of the interaction, the force that one exerts on the other, is proportional to the product of their masses and inversely proportional, divided by the square of the distance between them. So, note the difference between these subscripts, the mass of the first object and the mass of the second object, and this superscript, which is the, squared. Increase either mass or both, we increase the gravitational attractive force between them, separate them farther, we decrease the force of the gravitational attraction. When we measure the mass of an object, usually we end up measuring its weight and then calculating its mass. Mass is the thing we use to keep track of gravity. If you have a mass and I have a mass, then we are gravitationally attracted to each other, no matter what, because we are some distance apart. It means I am gravitationally attracted to the wall, to the floor, to this coffee cup, because I have a mass and it has a mass, and we are separated by some distance. That means I am gravitationally attracted to the car that's parked in the driveway, to that car that's parked in the driveway across the street, to that person walking down the street. And the way we keep track of the fact that that's a thing is by saying, I have some amount of mass. I respond to the gravitational attraction to other things according to my mass. In other words, mass is a way to sort of quantify a fundamental force, gravity. Gravity is a thing that, as far as we can tell, just happens. Happens to what? Mass. If you have mass, it is because you participate in the gravity story. So, like, mass is the way that we keep track of the fact that gravity influences you. The other thing that we use mass to do is to keep track of your inertia, and that's a related thing. But in this context, when we talk about mass, what we're doing is sort of keeping track of a fundamental force, a thing that just is true: gravity. Now that we have determined the proportionality constant, we can, and the way it took some years to determine it to any precision, and it took a very sort of painstaking experimental setup with a thin filament that was basically a huge dumbbell or a barbell, big masses on either side, was suspended from a very strong filament that twists. And another mass was brought nearby one of those large masses, and the twist that results when one of those masses was attracted to the other mass, that twist was measurable, and we could measure that way the attraction between the mass that's hung on that barbell and the other mass that we knew. Now that we have its value, 6.67 times 10 to the negative 11th power, we can help explain why the gravitational attraction between us and the coffee cup is zero. um, let's see, 100 kilograms, maybe 1 kilogram. I think it's less than that. So the numerator, mass 1 times mass 2, is 100 square kilograms. And if I put them a meter apart, and that's like, you know, a reasonable amount of mass and a reasonable separation distance for our own sort of day-to-day life situations. You know, the car has more mass than the coffee cup, sure, but we're on a scale, right? Roughly about the same kind of thing. I mean, the numerator has a value of 100. We're going to divide by 1 meter squared. So this fraction has a value something like 100 times 6.67 times 10 to the negative 11th. We're talking about a billionth of a Newton. That's nothing. That's like just this far away from being nothing. Let's say the car in the driveway is 1,000 kilograms. So we've got an extra factor of 1,000. Okay, we're still talking about a millionth of a Newton. I go stand next to the car. Compared to the force of gravitational attraction between me and the Earth, which is 100 kilograms times 10 meters per second squared, which is 1,000 newtons, the millionth of a Newton of force between me and the car is nothing. This is known as an inverse square law. It's proportional to the square of the distance. It's inversely proportional to the square of the distance between the two things. Strength or intensity is proportional, is 1 over the square distance. Even at great distances, as the distance gets larger and larger and larger, yeah, this fraction 1 over large becomes very small. 1 over 100, 1 over 1,000, 1 over, I don't know, 75 million. The larger the denominator, the smaller the fraction, but it's not ever going to be 0. There's nothing we can do to make this 0 except if one of the masses is 0, which is okay, sure. One mass exerts no gravitational force on a mass that isn't there. If there's nothing there, I can't pull it. If there are two masses, then it won't be 0. Here's an image to think about as we think about the inverse square law. Think about the a can of spray paint with a square cross section. So we're going to follow the edges of the square as it goes away from us. It's these lines that all the time form a square. Now those lines are straight. So in the same distance from can to this first sort of unit, another unit after that, this line moves the same distance away from the nozzle of the can. So we go from here to here, and then from there to there, and the horizontal distance that we move is the same for every individual unit. Which means we move one unit away, we go, think of it like half a square. Half a square to the right, the other line goes half a square to the left, the lines below go half a square, and we end up with a whole square. Go another unit. Okay, well, instead of half a square, the two lines go, one goes one square this way and the other one goes one square this way. So now we've got two squares between, but the other two lines went down. So we have 4 times the area that we had before. If we step another, now we're going 1.5 squares one way, 1.5 squares the other way. So that's 3 by 3. So we get 9. If we go another step further away, now one line's going 2 squares, the other line's going 2 squares, and we've got 4 between them. So it's 4 by 4. So we get 16 area units. If we compare the thickness of the spray of paint that we're getting, for, if we call this one layer, we take the same amount of paint but spread it over a bigger area so it's not as thick. And the thickness of the spray of paint, the coverage of paint that we're getting, that's like the intensity of the gravitational interaction. So it decreases by 1 over the square of the distance units that we move away. Here's a picture. At the surface, an apple weighs about a Newton. A radius away from the surface. Now we're twice as far away from the center of the Earth as we were. So our distance is twice as much, so that we square that, so it's 1 over 4. So if we were 1 Newton, now we're twice as far away, and we divide by 4 because we have to square the factor of 2. Here, we're 3 times as far away as we were. So the apple would only weigh 1/9 of a Newton. Here, we're 4 times as far away from the center of the Earth as we were when we were at the surface. So 1 over 4 squared, so it's 1 over 16 is what we would fill in here. 1 over 16 Newtons. If I want to exert a force on a thing, I gotta go, I gotta go touch it. I can't pick up one of those markers unless sci-fi, some kind of Jedi or something. But in the real world, I can't pick up one of those markers except by going over and touching it. How is it that how is it that the Earth is able to exert a force at all on this bottle cap? It's not touching the bottle cap. we call this kind of interaction action at a distance. They don't have to be in contact. And one of the ways we can think about sort of how to keep track of that is to define a field. Earlier when we was when we were yeah, when we were talking about escape speed, I said that if we were going fast enough, we could escape the gravitational influence of the Earth or the sun. And this is the same idea, that if you got some mass, the Earth, let's say, the Earth's mass creates in the space around it a field, a force field, a neighborhood or a landscape of possible interaction. Hand me some mass, put it in that landscape. Now the Earth can exert a gravitational force on that bit of mass that you put in its neighborhood. Now, technically, there's no point anywhere in space that is outside the neighborhood because we said it'll never be zero. But it could be small enough to be negligible, especially if we're already moving away, right? If we're moving fast enough, then we might be far enough away, and especially because now we know that the gravitational force decreases not linearly with how far we are, but you know, inverse square. So we decrease according to the square of how far we are. So if we double the distance, we decrease the force by a factor of 4. So as we get farther and further away, the gravitational force gets smaller and smaller and smaller quickly. And we might be going fast enough the other way that the force that does exist, isn't strong enough to cause acceleration enough to pull us back or to slow us down enough that we can get pulled back. It just might not be strong enough because we're too far away. And that's what we're talking about when we talk about escape speed. Not that the interaction is gone, right? The sun is still acting. The gravity of the sun is still acting on the Pioneer 10 probe, which left the solar system 40 years ago. Just not very strongly. Magnetic field is another example. We can, if I get 2 refrigerator magnets, I can push one without actually touching it, and we can say that that's an interaction that's sort of governed or moderated by a magnetic field. The region around one of those magnets that is affected by the presence of the magnet itself. Put another magnet nearby, we can act on it according to its magnetic field, the landscape of its influence. As these arrows, these field lines, get closer to the Earth, they also get closer together. And the closer together they are, that indicates the strength of the force. And the closer we are to the surface of the Earth, the stronger the interaction. So that's what about inside a planet? Well, if we're inside the planet, then there's some mass above us. Some mass of the planet is farther away from the center than we are. And we will be attracted to that mass just as much as we're attracted to the rest of the mass that's further towards the center than we are. The pull from the mass of the Earth below us, still closer to the center, is partly balanced by the mass that lives farther away from the center. Outside the planet, we know it decreases according to the inverse square law. But inside, it actually turns out to increase. Or if we start from the center, where there is all the mass of the Earth is away from where we are. So that side of the Earth pulls us this way, that side of the Earth pulls us this way, that side pulls us that way, and everywhere we are attracted to every direction equally. That means the net force on us is zero. So at the center, we experience no force, at least due to gravity. I mean, we would experience a whole bunch of pressure and heat and whatnot, but gravitationally, we could hang out there. If the Earth were, I don't know, hollow, we could exist at the center, just subject to no gravitational force, or certainly no net gravitational force. As we go through the solid material of, it's not actually hollow, I mean, as we go through from the center out to the surface, as we go, there's more mass concentrated below us than there is still above us. So we do end up feeling a net attraction until we feel the largest attraction when we are far enough away that we get to experience the entire mass of the planet below us, but no farther than that. Because if we go farther than that, then we start to increase the distance between us and that mass, and it starts to go like the inverse square decrease that we talked about. If we're standing on the surface, that's the farthest away, well, it's the closest we can be while still being as far away as all the mass of the Earth. Suppose you dig a hole. This means, and jump down. As you fall, your acceleration will decrease because the gravitational attraction, the net gravitational attraction, is less. At the center, the net gravitational attraction will be zero, but you will already have some velocity, which means you will overshoot the center and continue falling, but you'll be falling up. As you go, you'll be falling this way, but the gravitational attraction will pull you back towards the center. And if you jumped off the side from rest, then you will end up at the other side, just to the other side of the Earth before gravity pulls you back the other way. It's kind of weird to think about. This is a little bit of an unrealistic application of the sort of interaction with gravity. But there are other more realistic applications of these ideas. For example, tides. there are typically 2 high tides and 2 low tides each day. Is that because the ocean is just sloshing, or is it because of something else? And the answer is it's due to the gravitational attraction that the moon exerts on the water. Because the 2 bulges, we pull water down from the poles towards the equator. Because those 2 bulges are on the opposite sides of the Earth. That's half a rotation. That's every 12 hours. So in general, in 24 hours, we get a high tide every 12 hours. But if we've pulled water around that way, that means there's a little bit less on either side, I think. Pulled water down, attracted to the moon. There'll be a low tide somewhere else. Oops. But that's not the only attraction that affects the tides. Sometimes the gravitational effects of the earth of the moon and the sun combine to produce pronounced tides called spring tides. When we say pronounced tides, we mean the difference between high tide and low tide is the largest. Now, if the moon is halfway between this point and this point, then the lunar effect is going to partially cancel out the solar effect, or vice versa. The solar effect partially cancels out the lunar effect. The moon is much closer, so its effect, well, but the sun is much larger. But we know that the gravitational force is inversely proportional to the square of the distance and only proportional to the mass. So I expect the distance to matter more, and the moon's effect to dominate. But the sun in this configuration would partly cancel the effect of the moon. So the differences between high and low tide are not as pronounced. We call them neap tides. Other implications for our new understanding of gravity. Suppose we were in some sort of rocket ship that was traveling at 8,000 meters per second near the Earth in circular orbit around the Earth, like we talked about. We would be in circular orbit not because we're driving in a circle, but because we are falling in a circle. We fall all the time according to the gravitational attraction. So we are constantly falling we experience in that 8 km/s circle orbit around the Earth, we experience exactly the same sensation as we do when we jump off a diving board. Jump off a diving board, close your eyes. Ignore the air that you feel moving past you. There's nothing holding you up. We feel weightless. That sensation that happens when you're driving and you drive over a hill, and at the top of the hill, or in a roller coaster, at the top of the hill, you feel like your insides have floated up in your body a little bit, and there's like a nausea or like an unsettled stomach kind of feeling. That feeling has to do with the fact that just for a second, as you come around the top of the curve, you're moving down, and you're moving in exactly the way that gravity wants you to move because you're in the car. So gravity isn't it doesn't need to pull on you anymore because you're already doing what it would want you to do in the first place. You're falling, so don't you're falling and the car is falling. So the car doesn't need to hold you up. And the different sort of levels of your body don't need to hold up your other organs because they're falling, and you're falling, and the whole thing is falling, following a little bit the curvature of the road. The car and you are moving exactly the way gravity would want you to. So the car doesn't need to do anything to you because you're going to follow the car anyway because you're influenced by gravity just like the car is. So you feel the car seat or the roller coaster seat pushing on you less. And if it's going fast enough around this curve, you could feel weightless because we could define weight, sort of the perception of weight, as the force that we exert on the surface holding us up. So I can perceive my weight. My weight is the force that I exert against the floor. And the floor is holding me up against the force of gravity. I'm not accelerating. So I feel a force equal to my mass times the sort of surface level acceleration due to gravity. What if I jump? If I jump while I'm in the air, I'm not touching the floor anymore. There is no supporting surface, so I don't exert a force against it, which means it doesn't exert a force on me. So for a second, I don't feel my own weight. Like on a trampoline. It's a little hard to feel if you're just jumping on the floor because you don't spend enough time. You know you're going to hit the ground. But on a trampoline, you spend a little bit more time in the air, and you can start, especially at the top, right? Right at the top of your jump, when and you can it sort of unbalances you, that you don't feel that support anymore. The spaceship that we're in is like the car, like the roller coaster. The spaceship is falling. We just happen to be going horizontally fast enough that we never hit the ground. But that doesn't stop us from constantly falling. If we are constantly falling, then we are constantly in that state of feeling like there's nothing holding us up, because the spaceship doesn't, if we're sitting in the seat in the spaceship, it doesn't need to hold us up, because we are falling exactly the same way that the spaceship is. There's no reason for the seat of the spaceship to have to push us at all, because it's falling the same way we are, subject to gravity. It doesn't need to change our direction. It doesn't need to counteract our gravity, because it's moving according to gravity. And astronauts in orbit are weightless in that sense. They are constantly in free fall. They just happen to also be going fast enough to miss the ground. Einstein's sort of approach to account for this is to imagine the gravitational field that we talked about as actually changing the nature of space nearby. A bowling ball would make a dent on the surface of a rubber sheet or a waterbed or something. That dent is is true for all things that enter that region, all things that enter the region of the gravitational field of that massive ball. So if we go nearby, we roll downhill. Einstein's Einstein's idea essentially is to compare if I'm in a spaceship and I'm holding an object and I release that object and it goes nowhere. It just hangs out in front of me. I can't tell the difference between the whole spaceship falling due to gravity. I can't tell the difference between that kind of weightlessness and the absence of gravity. If the whole thing is at rest, if there are no forces acting, I release the object and it just, nothing pulls on it. Nothing pulls on me, nothing pulls on anything. Just here we are. And if I'm inside the spaceship, I can't actually tell the difference between that situation and the situation of orbital motion. That's that equivalence, that one perspective on things, that I'm falling due to gravity, and the other perspective that I am in a situation that is entirely devoid of force, and I can't tell the difference. That one or the other perspective is entirely true. That's relativity. When we talk about Einstein's theory of relativity, what that really means, relativity, is that either perspective has to be correct, that the laws of physics and the way things behave has to be true for either perspective, for either observer. And then when we talk about relativity, that's really what we're talking about. Since we're discussing these sort of abstract ideas, suppose that massive ball on the waterbed was dense enough, massive enough in such a small space. Now, if we put somebody on the surface of this star, they experience a force according to their mass and the star's mass and the distance between their mass and the center of mass of the star, which is the radius of the star. If the star shrinks without losing mass, so the numerator stays the same, but if we decrease the size of the star, if we decrease the radius, half what it was, a factor of half in the denominator squared is like an extra factor of 4. So the force on that person on the surface, assuming they weren't destroyed by that much force, is 4 times what it was. This, as pictured, isn't a black hole, but it's possible that the object has enough mass in a small enough space, small enough volume, I suppose, with small enough size, that the escape velocity that would be required is greater than the speed of light. That the velocity we would need, the speed we would need to escape the gravitational field created by that object, that the escape speed is greater even than the speed of light. We will not be able to leave. Light will not be able to leave. So we call it it's a hole because everything that is in the gravitation, subject to the gravitational field, gets pulled to the center, and the shape of space is warped so much by that much gravity that it's just gone. It just, like, can't get at it because we can't get anything back out. So it's a hole. And we say that it's a black hole because the light can't get out. It's literally not lit. We see things because we shine light at it and the light bounces off. We cannot see a black hole that way because the light that we send to it does not bounce back. We can, if we sort of look sideways, we can see light bend if it gets a little bit too close. But if we try to look right at it, that light is gone. Everything attracts everything else. Universal gravitation. We said this is the Newtonian thing, the law of universal gravitation. Why is the Earth round? Because all the mass attracts all the other mass. It's symmetric. The surface is equidistant from the center. That's a sphere. Yeah, to a pretty good approximation, it's a sphere. The universe is observed to be expanding and accelerating outward. It's expanding and speeding up. And that is a very interesting problem. It's in many ways on the forefront of sort of astronomical or cosmological research, because it doesn't make any sense. When you encounter things about dark matter, there doesn't quite seem to be enough mass that we have observed anyway further out in the universe to account for the expansion, the acceleration away from other things. This expansion and acceleration is really interesting phenomenon in the context of universal gravitational attraction. What would cause it to speed up? It's a like I said, it's an open question. We we can talk about how the history of science sort of proceeds like a spiral, like a helix. We have our terrestrial observations about projectiles, and then we have our celestial observations that Kepler is making, and then we can put them together, come circle back around, but make some progress. And we have Isaac Newton, and we can talk about the law of gravitation, the law of universal gravitation, and then we work with the consequences of that for a little bit, and we've spun around, and now we're talking about Einstein, and now we're talking about black holes, and now here we've observed, or at least found evidence of black holes. It was in the news a little while ago that we were able to sort of with photographic processing, we were able to obtain something like an image of the like influence of a black hole, the corona around a black hole. So, but now we have, based on the new observations we can make about our new understanding, and we keep sort of spiraling, making some progress. But here we are with these observations. The universe is expanding and accelerating outward. And we're like Kepler. We have the data and we can say, look, I can show you that it's expanding, but I don't know why. It's an exciting place to be, because that means there's another why out there to find. Pretty cool. Right? A little bit of science fiction there right at the end. I know this was a long video. Appreciate your going through it.